So let's take a look at this fractal. This is a pentagon fractal, right? And you're going to be given this code, right? And what you're going to need to do is you're going to have to adapt it to your polygon, regular polygon. But right now, this is a pentagon. So uh, if the options you're going to have, if you run this, let me go to this first function right here, is that you can set the offset. So with a zero point 0.5 offset, as you see over here, that edge, the next pentagon is 50% away from the vertex of the previous, right? If you set this to zero point 0.1, then you're going to get less of a distance, you see, so that's like 10% from the of the side, of that side, right? You could also set the number of recursions, so if I go higher, a little higher, I'm going to get some more, 30, let's see, 100. What happens with 100? Okay, so it starts to get really, really small. So maybe 50 would be a good one, right? Looks pretty good. And of course, fractal, the as you zoom in, you get the same representation. Okay, so let's take a look at how this is organized, right? So I'm going to go to this document and I'm going to do an example of a pentagon. So the first thing I have to do is I have to draw these vertices, right? So I labeled them here vertex 0, 1, 2, 3, and 4, right? And I know in a pentagon, the angle from V to the center and to these vertices is 72. So I know this is 36. So I can calculate my L. I need L because each of these vertices is equidistant from the center, right? So I need L. Well, it's sine of 36 over half of the side, right? Half of the side, whatever the side is, over L. So that means L is equal to 0.5 S over 36. Well, that's what I have over here, right? So you see, that's my equation for L. Now, these have to be in radians. So when I do an angle, I always label it and convert it into radians. You can't use degrees here, right? So this is just an angle converted into radians. Okay, so now I'm going to put this at 0 just to show you, oops, just to show you what's happening here. I'm going to put this at 0 and I'm going to just do one of these. I'm not going to do all of them. So if I do at 0, you see that pentagon, I'm starting at 0 here. So that's my first vertex right there, right? Second, third, and fourth. So what I wanted to do is I wanted to start at the top. So I set this one to 90. So that means the first vertex would be at 90 degrees from the center, you see. So anyway, you don't have to do this for all of them, but it works for the pentagon. So what do we do? So what we do is we take each of our and we calculate using trigonometry, right? So if you go over here, you look at the angle. So you have your angle from the center. Remember, 90 was for me the first vertex. So I add 72. To get the next one, I add 72, 72, 72. So I go all the way around and I get all of my vertices, right? So that is all the vertices. The next is we have to add them to this array, and then we have to make the edges, right? So just to show you without the edges for a second, if I comment that out, and you see there are those points, right? So what the edges do is they connect the points. So you have to give me the index of each vertex, 0, 1, right? 0, 1 would be that line over here. 1, 2, 2, 3, 3, 4, and then 4 has to go back to 0. So when you get to 4, vertex 4, you got to get back to 0. So that makes the edges. You see, there it is. So the next part is we want to make uh, the next polygon, right? So if I go to my picture here, it kind of looks like this, right? So this is the next polygon, right, or a pentagon, and it's inscribed, right? So you're given x, which is the offset, and we want to calculate the theta, the rotation that we need to do of this new pentagon, and also we need to know its size, right? So it fits in perfectly. So you're given x, which is your offset, and we have to calculate theta. Okay, well, it's really not too bad, right? If you look at this triangle, I can calculate s using the law of cosines, right? Law of cosine. I know this angle in the pentagon is 108. So I'm using my law of cosines to find s prime, which is the new size, and there it is, right? And then if I want to find theta, now that I have s, is just a law of sine. So sine of theta over sx and sine of 108 over s prime, right? So that's how you calculate those two for the next polygon. So if you take a look, I have the offset, my s1 and s2, right? Those are the two parts of the side. And there's my law of cosine, and there's my law of sine. And then I send it into the recursion, right? So the recursion will make more of them. And my angle is each new pentagon is going to be rotated a certain amount. So the first one will be 0, and the next one will be, the addition of theta. So let's go to the recursion. So I'm just going to do one recursion right now. I'm going to go 0.2, and I'm going to do one recursion. There, see? Let me make it zero point 0.5 just to get some difference here, right? So there it is, 0.5. So here's the recursive function, right? So you're getting all this information. You don't have to touch anything here. And this is the same as before, right? So we just make the pentagon. Now, I'm going to comment this out, and I'll show you what this part does. If I just comment this out, let's see right here, 1 2 3. So you see we made the pentagon, but yes, it's great, but we have to rotate it, right? We have to rotate it, and that's what this does, right? So you take your angle. Remember, we started at 0 for the first one, so add theta, right? Remember, we calculated. So this takes the every point and rotates it, and there's a formula for that right up here. So this is a formula rotating a point around the origin. So it will rotate every point. So if I run it again, you see it's been rotated. Now, everything is set here in terms of the angles. And let me just increase this to 8 maybe. And you see we just keep on going, right? So the only thing, like I said, you're given this code. The only thing you have to do is you're going to have to change for your polygon. You have to change these angles, and they're going to be the same for a hexagon or an octagon, right? Then you're going to have to also calculate this internal angle for your polygon, right? And you're going to have to possibly add some more points if you have. Well, I go down here. If you have a hexagon, you're not going to have 5 points. You're going to have 6 points. So there's going to be a couple of changes here, right? But that is what you're expected to do.